All right. Are we rolling? All right.
Yeah, I think he's great.
Ladies and gentlemen, I welcome you to Black Hole Month in honor of recent developments with us actually getting to peek at the event horizon of a black hole. We had the good fortune to have a couple of really exciting talks about black hole science. And the first is Dr. Ed Cackett. Ed Cackett grew up in the suburbs of Manchester, England, studied physics at the University of Durham before pursuing his PhD in astrophysics at the University of St. Andrews in Scotland. After that, he spent 4 years as a postdoc at the University of Michigan, where he was a NASA Chandra Fellow, and then 1.5 years as a research fellow at the University of Astronomy, Institute of Astronomy, University of Cambridge. In 2012, he made the permanent move back to Southeast Michigan to become a faculty member at Wayne State University, where he is currently an associate professor. He has published over 150 articles in peer-reviewed journals. He is an expert in X-ray observations of black holes and neutron stars, and this is, I believe, his third presentation for us. So please welcome back Dr. Ed Cackett.
Thank you for having me back. It's very nice to be back here. Good to see some familiar faces. And today I will talk to you about my research about black holes. So I'll be talking about how we can apply indirect techniques to figure out what happens when things fall into black holes with a technique we call reverberation mapping. This is work that I've been doing for the last few years at Wayne State University with colleagues around the world. So, to talk about black holes, where do you start to talk about black holes? Well, you have to start by talking about gravity, because that's what black holes are all about. So, to understand what a black hole is, we need to understand what it means to try and escape from gravity, right? So how do you beat gravitational attraction? Well, you need to be traveling fast enough. So you need to be traveling fast enough to be able to escape away from a body with a given mass. So if you want to be able to, for instance, leave the surface of the Earth and get into orbit, you need to be traveling the escape velocity for Earth. And the escape velocity for an object is the one and only equation I have in the entire talk. Depends on the mass of the object, m, Newton's gravitational constant, and then the radius of the object. So, the bigger, the more massive the object, the higher the escape velocity, and the smaller the object, the higher the escape velocity. So, high mass objects that are very small are going to have a high escape velocity. So, we can plug the numbers in for Earth. Find that you have to travel at 11.2 kilometers per second to be able to escape from the Earth's surface and away from the Earth's gravity, which is 25,000 miles per hour. You can plug in the numbers for the Sun, and you get 1.4 million miles per hour. And so you could ask the simple question, well, what if I just arbitrarily turn up the mass and turn down the radius? Can I get speed? What parameters do I need to have a speed where the escape velocity is the same as the speed of light? And when that happens, what are the consequences, right? What if the escape velocity is greater than the speed of light? What does that mean for us? Well, it didn't actually take long after Isaac Newton had come up with his theories of gravity for astronomers to actually start, or physicists to actually start asking these questions. There was a Cambridge physicist called John Mitchell in 1783, and Laplace was asking similar questions at the same time about exactly this question. What happens if you have an object that's big enough that its escape velocity is greater than the speed of light? And this is a page extracted from a letter that he wrote to the Royal Society in London in 1783. You can see this is page 50 of a rather large, long letter. But this is, of the entire letter, this is the only thing that anyone ever remembers. This is point 28 he's making in this letter to the Royal Society. And he says, if you were to make an object 500 times bigger than the Sun with the same density, it would have an escape velocity that's greater than the speed of light. So he's actually conceived the idea of a black hole here for the very first time, although of course he didn't call it a black hole. And this is the idea of an invisible or a dark star. In fact, it turns out we actually decided it was pretty boring. And if you go a little further down here, you can read that he realizes that to be able to, because you wouldn't see any light from this object, you could figure out it was there just from the motion of any body that's emitting light. So if you were to be able to see the motion of a star around such an object, you would see it. He figures that out down here. And then he says, the consequences of such a supposition are very obvious, and some consideration of them are somewhat beside my present purpose. I shall not prosecute them any further. In other words, I've discovered black holes, but they're boring. And it's really pretty trivial and obvious. So I'm not going to talk about it anymore, right? So that's all he mentions about this idea in a rather long letter. As I said, this is what the only thing anyone ever remembers about this letter is the Royal Society. Of course, our modern day view of black holes certainly not trivial, and our understanding really comes from Einstein, right? And Einstein, of course, came up with the theory of general relativity and gave us the understanding that an object with mass will bend space and time. And so, in the typical way we try and show this graphically is to show space as being some flat surface that's a grid. Think of like a trampoline. And if you have an object of mass that you put on a trampoline, like a bowling ball, it will curve the trampoline, right? And if you were to roll a ball along a trampoline without any object on it, it will roll in a straight line. If you roll a ball on a trampoline that has a bowling ball on it, of course it won't roll in a straight line anymore, it will roll on a curved path, because the surface that it's rolling on is curved, right? And that's Einstein's basic idea of what will happen to any object that's traveling near another object with mass. Of course, it doesn't happen to an object, it will also affect light. Any light that's traveling on space that's curved will also travel along a curved path. And so that has consequences for black holes. So we show this analogy for how space is curved, but really, of course, space is three-dimensional, and so it's actually more nicely shown, I think, in this little movie here that it's been extracted from a little documentary that the American Museum of Natural History did. So hopefully this should start. So you can see, really, space is getting bent in a three-dimensional way. You have two objects coming towards each other, you can see what happens. And then the Earth, or an object passing by an object with larger mass, with curved space, will travel along that curved path. So this is the idea of how we think objects with mass affect space, and that, of course, has consequences in terms of black holes. So how do we picture a black hole in such an idea where we have curved space? Well, let's think about objects that are less extreme to start with. Let's think about the sun, right? It really is just making a little dent in space like a bowling ball on a trampoline. Okay, we can go to more extreme objects, so like a white dwarf, so a Earth-sized object that's about the mass of of the order of the mass of the sun. You get a much deeper dip in space. Think of even more extreme, and go to a neutron star, which has a radius about 10 kilometers, the size of a city, with a mass, again, similar to the sun. And you get a much more extreme dip in space. In fact, the escape velocity for a neutron star is something like 30% to 50% the speed of light. Gravity around a neutron star is so extreme that you can actually see 70% of the surface, because light from the back gets bent round to the front, right? So you can see more than just a hemisphere on a neutron star. What about a black hole? Well, a black hole is where space and time is so extremely warped by the infinitesimally small, dense object that it's really a rip in space. And we define this region here, the event horizon, where the escape velocity is equal to the speed of light. So if you're outside the event horizon, you still can escape from the black hole, right? As soon as you cross the event horizon, not even light can escape. So it's the point of no return. We think of black holes then typically in terms of how can we observe a black hole. So that's how can light escape from a black hole from outside the event horizon. As far as we know, so far there's no observable way of us really seeing beneath the event horizon. Okay, so how can we go about characterizing a black hole? Now, it's actually extremely simple to characterize a black hole. Much more simple than characterizing, say, this auditorium. So if I wanted to characterize this auditorium, I would have to first start by, say, measuring the size of the room, counting the number of chairs, the number of people in here. If I was really wanting to do it properly, you'd actually start, say, figuring out the number of molecules and air that's in this room, and you end up with a huge list to be able to properly characterize this room. Well, what do you need to characterize a black hole? You just need two things, right? You need the mass of the black hole, and then you need the spin of the black hole. Because as you know, almost everything in space has some spin, right? Has some angular momentum, and so black holes end up having angular momentum. Technically, black holes can also have a charge, but if we were to have a charged black hole, it would very quickly become neutral by attracting some charge of the opposite charge, and you end up with a neutral black hole. So, for all intents and purposes, astrophysical black holes have no negligible charge. So we say that black holes have no hair, right? They're not complicated by things. They just have a mass and a spin. So if we want to learn about black holes, you just need to measure mass and spin. So what do we know about their masses? Well, there are several types. There are stellar mass black holes. These are black holes that are about 10 times the mass of the sun. I'll talk about how those are formed in a few minutes. And then there are supermassive black holes. And these are black holes that are millions to billions of times the mass of the sun. And they seem to reside at the center of every major galaxy in the universe. So how do we form black holes? How do we get such extreme objects in the universe? Well, if we think about stars, stars are objects that are in balance. They have gravity, the force of gravity pulling the material in, but they also are emitting light, and that light gives you a radiation pressure that's pushing outwards. So you have a balance between gravity pushing in and radiation pushing outwards. And so a star like our sun is sitting in the balance always, where gravity is balancing radiation. However, at the end of a star's life, when nuclear fusion stops, then the radiation turns off, right? And once the radiation turns off, gravity wins out in that battle between gravity and radiation, and the star will collapse. If the star is massive enough, then you end up with a supernova explosion, and if the star is something like 20 times the mass of the sun or larger, we think that we end up forming a black hole. Now, of course, you cannot mention the word supernova without gratuitously showing some supernova remnant pictures. So I'll quickly show my favorite supernova remnants. Here is supernova 1006. This is observed by the Chandra X-ray observatory, and I think the orange and yellow light here is from optical. This is really hot gas. It's still hot 1,000 years after the explosion took place. That's plowing into the interstellar medium, forming this sharp front here. Another favorite of mine is Tycho supernova unknown. This again is an image from the Chandra X-ray observatory. This explosion was in 1572, and it's still expanding today. In fact, it's expanding at 5,400 kilometers per second. How do we know that it's traveling so fast? We can visibly see it increase in size. So this is the image in the year 2000, and this should be a little animation over a period of about 15 years. And you can see it move. Right?
Wow. Oh God, it's coming from us.
So, we can actually measure the expansion rate, and the fastest expansion rate that they measure is 5,400 kilometers per second. Even 500 years, almost 500 years after the supernova explosion. So, these explosions can end up leading to forming black holes. But how do we go about seeing a black hole? Well, we've heard a lot about the direct way of seeing a black hole recently, and I'll mention that in a few minutes. But most of my talk is going to be focused on how can we indirectly see black holes, right? And John Mitchell in 1783 told us, right? The answer is just gravity, right? Why we can't see a light from the black hole itself, we can see the effects of gravity from the black hole. So we can, for instance, see orbital motions of stars near a black hole. If a black hole is in a binary system, we can see the motion of the normal star that's orbiting around the black hole. I'll show you in a moment the motions of stars at the center of our own galaxy, where we can see the motions of the stars orbiting around the supermassive black hole at the center of the Milky Way. And the way that I'll focus on my work, my research is focused on, is looking at light that's falling into a black hole. So black holes, because they're so massive and dense, their gravitational pull means that they can rip stars apart. We can see that material falling into the black hole. It's a very efficient way of actually leading to the emission of radiation, as I'll talk about later. And we call this process accretion. And through accretion, we can actually see light coming from the gas as it falls into a black hole. Before I talk about that, I think until a month and a half ago, what I'm about to show you was the best observational evidence for the existence of black holes, and that's the motions of stars in the Milky Way. So here is a little movie from the European Space Observatory, European Southern Observatory, sorry. Here's the Milky Way, of course. We're going to zoom in. This is with real data taken by the European Southern Observatory. We're going to zoom in to the very center of our own galaxy, the Milky Way. So we're zooming, and we're going to keep zooming.
God, it's full of stars.
And we're going to keep zooming.
Yeah.
And eventually, we're going to peer through the dust that's actually in our way. When we look in infrared light, you can see the light from the stars and the cluster of stars at the very center of our galaxy. And you can actually see the motion of stars and even the motion of a gas cloud around the Milky Way, the center of the Milky Way. The center of the Milky Way is called Sagittarius A star, and that's the name of the black hole that's there. So I can show you a false color, what I think is a nicer false color image, animation of the stars at the center of the Milky Way. Here are the stars. Keep your eye on S02 and S016. See, 16 gets slingshotted.
Yeah, well, there it is.
S02 does an entire orbit in a period of about 15 years. Right. So these stars are orbiting around an object that's not emitting any optical light or in an apparent dark part of space. So you can actually just use Newton's laws and Kepler's laws and figure out the mass of the object at the center, and we find that there is a black hole at the center of our Milky Way that's 4 million times the mass of the Sun. This is work that's been led by Andrea Ghez at UCLA and Reinhard Genzel at the European Southern Observatory. Over the past 15 years, they've been putting a lot of time and effort into monitoring these stars and really accurately measuring the positions of these stars. It's a very tricky technical thing to do, and they did incredible work to be able to get these measurements. And of course, the motions are not just two-dimensional, as that animation showed. They're actually three-dimensional. There's enough data now to be able to figure out the full three-dimensional paths of all these stars in this cluster at the center. And so here ours is the paths of all those stars now in a three-dimensional manner, and you can see they're orbiting around the black hole here at the center. All these stars seem to be nicely orbiting around here. And as you go further out, the motions become a little more chaotic. You see that, it's really quite incredible the amount of information they've managed to get about the motions of these stars around the center of the Milky Way. So, up until a month and a half ago, this was the best direct evidence that black holes exist. But all that changed, of course, with the Event Horizon Telescope. So before I briefly talk about the Event Horizon Telescope, let's just ask the question, how big is Sagittarius A star, so the black hole at the center of the Milky Way? So we know its mass. Its mass is 4 billion solar masses, and we can calculate the size of the event horizon. All it does is it just depends on the mass of the object. So if you plug the mass in, you find that the event horizon for Sagittarius A star is 12 million kilometers. So that's 0.08 AU, astronomical units, which is 39 light seconds. The distance it takes light to travel in 39 seconds. We can also figure out the angle on the sky. The distance to the center of the Milky Way is about 8 kiloparsecs, or 27,000 light years. And we can plug the numbers in, and we find that that angle is 6 times 10 to the negative 9 degrees, so 6 billionths of a degree, which for those of you who are familiar with arc seconds, that's 22 micro arc seconds. Right? So, just to give you an idea of how small that is, typical optical seeing at the best sites in the continental US, you're lucky to get much better than 1 arc second, right? So you need to be able to get, 100,000 times better than what you can do from the ground with optical observations, typical standard optical observations, to be able to image the event horizon of Sagittarius A star. So at this point in my talk, I used to show this slide that said, could we image a black hole? And I'd show this simulated image of a black hole and what the Event Horizon Telescope was supposed to do, and tell you, well, let's just wait, we'll see what happens, right? Of course, now I have to throw this away. As of April 10th, I'm sure you've seen this many, many times now. Here is the image of the first direct image of a black hole shadow. So, of course, it's the image of the light coming from M87 star, which is the black hole at the center of M87, a relatively nearby galaxy that has the largest event horizon of any. The largest angular size of any event horizon for any black hole. And so was one of the first two targets they looked at. They looked at M87 and they looked at Sagittarius A star. And so from this, they were able to measure the size of this emission ring to be 42 micro-arc seconds. And that implies that the black hole at the center of this galaxy is 6.5 billion solar masses. And we are still waiting on the results that they got from Sagittarius A star. Some beautiful things about this, you can very clearly see the hole, right? The shadow of the black hole. It's because light can't pass through the black hole itself. It just gets captured by the black hole. You also get an effect called the photon ring, where photons can actually get trapped in the gravity of the black hole and travel in a perfect circle. We see that it's brighter down here than up here. This is because of Doppler effects, essentially relativistic Doppler effects. So the material here is actually moving towards us, which means it's brighter. Makes it brighter. The material up here is fainter because it's moving away from us. And so we can actually tell that this black hole is spinning, right? And which way it's spinning, right? So it's sort of going like this, right? Into the screen and out at the top and out of the screen at the bottom. To give you an idea as to why this looks like this, the Event Horizon Telescope team made this rather nice animation. So this is a zoom in into an animation of zoom in into M87. As you get closer in, you can see the material falling into the black hole and the jets that get spat out. And if you look in sub-millimeter wavelengths, you can see all the way through this down to the black hole at the center. And some of these photons falling into black holes, and the others that don't fall in get bent round by the gravity. And for an observer over here, you only see the ones that get bent towards you. And so you see the photons that come towards you that are bent towards your line of sight by the black hole's gravity. And you don't see the ones directly that fell into the black hole. And that's why we see the image that we see of this first direct image of M87. So, M87 and Sagittarius A star are so far going to be the only two objects we have a hope of being able to do this with. They have to do upgrades to the Event Horizon Telescope to do any others. So at this current time, to be able to get a significant sample of looking at black holes and figuring out how things fall into them, we have to rely on indirect techniques. And that's where the sort of studies that I do in terms of accretion and material falling into black holes comes in. So as I said before, accretion is where gas is either getting pulled off a star or is surrounding the black hole. It falls into the black hole because everything has some sort of spin, some angular momentum. This ends up forming a disk of gas that spins around and falls into the black hole. And as it falls in, gravitational potential energy gets converted into radiation, and we see lots of radiation coming from these objects. In fact, the process of accretion of gravitational potential energy getting converted into kinetic energy and into radiation is more efficient than nuclear fusion, right? So nuclear fusion, which powers stars, is less than 1% efficient. In the sun, we have hydrogen going to helium, and we end up giving 0.7% of energy back. We get back in terms of how efficient that process is. We can do this in terms of what energy we get out from material falling into a black hole. And in fact, it turns out that about 20 times more efficient than nuclear fusion, right? So this is a really efficient way of producing light. So things falling into black holes turn out to be some of the brightest objects in terms of their luminosity in the sky. And these were first, of course, discovered, this sorts of objects were discovered known as quasars, or alternatively known as active galactic nuclei. One of those objects was M87, the one we just talked about. This is M87. Here is the light from the accretion disk, the glowing nucleus of the galaxy. And here is the jet that's getting spat out from close to the black hole and traveling millions of light years out into intergalactic space. What you can see here is that the light from the center of the galaxy is outshining the rest of the stars in the galaxy. Right? This is typical of what we see in active galactic nuclei. Right? So we have as much light as say something like 10 billion stars coming out from the very central nucleus of the galaxy. And the only way you can do this, produce that amount of light from that smaller space, is from this process of accretion. And you can play games and ask questions about, is this really the only way to do it? Can you power this in any other way? Can you do it, for instance, just by making a really large star, nuclear fusion? Or can you do it by having a really dense cluster of stars? And this is a famous flowchart that famous astronomer Martin Rees created, that basically says, however you try and do it, whether you have a big gas cloud that makes a super big star, or you have lots of stars, the bottom line is massive black hole, right? So whatever way you try and get as much light as 10 to the 10 stars coming from such a small space, end up forming a supermassive black hole. There's no way around it. And so, over the last 20 years, we've actually learned a lot about black holes in galaxies, at the center of galaxies, and their connection to the galaxies themselves. And we found it seems to be a profound connection between the supermassive black holes that reside in the center of the galaxies and the galaxies themselves. And we now know that basically all major galaxies in the universe seem to have a supermassive black hole at the center. And the galaxies know about that black hole. Right? And this is actually remarkable, because the black holes themselves are, say, 10 to the a billion times the mass of the sun, right? But the number of stars in the galaxy is many, many times larger than that, right? The mass of the black hole is something like 0.1% of the mass of the galaxy. So the mass of the black hole is insignificant when compared to the mass of all the stars. The black hole itself is also small, right? The event horizon, the black hole, is smaller than the size of the solar system, right? So physically it's small. In terms of its mass, it's inconsequential, right? Yet there is a tight correlation between what's plotted here is the mass of the black hole, and what's plotted along here is essentially the mass of the stars in the galaxy. A measure of that. And you see, it's for an astronomical correlation, this is about as good as it gets, right? Bigger black holes reside in galaxies that have bigger bulges, right? And this is remarkable. The black hole, as I said, is small in terms of its mass and small in terms of its size when compared to the galaxy as a whole. And so the two things know about each other, and they must evolve together. So you can then ask the chicken and the egg question, right? Which grows first? Does the black hole grow first and affect the growth of the galaxy? Or does the galaxy grow first and affect the growth of the black hole? And there now seems to be evidence that a process called black hole feedback, where accretion onto black holes affects the galaxy in terms of being able to turn on or turn off star formation. And we can actually see that when we look at observations of galaxies with big black holes. Does anyone know what this is? What this is an image of?
1275.
1275, yes. This is the Perseus cluster, and this galaxy here, the very center, is NGC 1275.
Nicely done, Doug.
Yes,
I imaged that a couple months ago.
It has these beautiful filaments in H-alpha, so if you want ever do it with an H-alpha filter, it looks beautiful, right? So this is the optical image of NGC 1275. It has an extremely massive billion-type solar mass black hole at the very center. And when we look at X-rays and at radio wavelengths, you see something quite different. So here is an X-ray image. The white is the X-ray emission, and it's the X-ray emission from the hot gas that sits in the galaxy cluster. The size of this image is about the same size as the optical image I showed you before. Right? So there's a lot of hot gas there. But what you also see are two bubbles, right? Two empty spaces where there isn't any hot gas, or there's less hot gas. And that correlates with the radio emission that we see from the center NGC 1275. So these are radio jets that are getting plowing into the gas in the intergalactic medium outside NGC 1275. And you can see that it's actually made holes in where the hot gas is, right? It's blowing bubbles in the gas in the center of this galaxy cluster, right? So the jets from the black hole are affecting the galaxy cluster as a whole and helping shape the galaxy cluster and shape what's happening in NGC 1275. This is direct evidence for the supermassive black hole at the center having a direct effect on the galaxy that it sits in. So understanding how black holes feed, right, and grow is super important for us understanding how galaxies grow. The two things are tightly connected. So how do we go about doing this and actually getting right down and seeing what happens to this material when it's just about to fall into the black hole, right? How do we get down to the event horizon? We have to be able to see that accreting gas. So we rely on the fact that it's hot. And as you know, everything that's hot emits radiation. And it turns out that the wavelength of the radiation that emits just depends on the temperature. So if we think about humans, humans have a body temperature of 37 degrees Celsius or 98.6 degrees Fahrenheit. And so we are currently all filling this room in infrared light, right? We're glowing in infrared light. This is why night vision goggles work, right?
I can see you glowing.
The sun is a little bit hotter, about 6,000 degrees, right? And so it radiates mostly in the visible part of the spectrum, right? So it peaks in about the green part of the spectrum. You can go hotter and hotter, right? And hot accretion disks of materials falling into black holes. They're millions of degrees, and so they radiate in X-rays. So if we want to see stuff falling into black holes, we need to use X-ray telescopes. And if you look at the X-ray sky, it does not look like this. This is, of course, the Milky Way in optical light. But if we do the same image in X-rays, what do we see? Well, you still see the plane of the galaxy, right? But now, instead of seeing regular stars, what we're actually seeing is gas falling into neutrons, onto neutron stars or into black holes. As well as other objects like supernova remnants and other extreme objects that emit X-rays. So predominantly what we're seeing here are the binary systems in our galaxy that have a neutron star and a black hole that's actively accreting. Right? So X-ray eyes give us black holes and neutron stars, whereas optical eyes just give us regular stars. So we want to look at black holes, we need to go into X-rays. So how do we do X-ray astronomy? Well, we're thwarted by the atmosphere, right? The atmosphere blocks X-ray and ultraviolet light, of course. This is a good thing. If we didn't do this, we'd all have skin cancer pretty quickly. But it's a bad thing for those of us who want to study black holes, because it means we have to spend lots of money launching things into space. To be able to get above the Earth's atmosphere, to be able to see X-rays from space. And the sort of workhorses that we've had for the last 20 years have been Chandra and XMMNewton. And these were actually launched 20 years ago this year, 1999. And their 20th anniversaries are coming up. Chandra was predominantly a NASA mission led by NASA. XMMNewton was led by the European Space Agency. Both agencies worked together on launching both of these missions. Chandra has its mirrors up here and the detectors down here. These are, of course, the solar panels. It has extremely good accuracy in terms of its imaging capabilities. It can take images with a resolution of 1 arcsecond, right? So as good as you can get from optical imaging from the ground. Right? XMMNewton sacrifices its angular resolution. It's more like 15 arcseconds, if I remember rightly. that may be a little off with that number. But instead it has 3 X-ray telescopes that collect a lot more light. So it's a bigger light bucket, but less good at imaging, making pretty pictures. So depending on exactly what you want to do, depends whether you choose Chandra or XMM. X-ray telescopes, of course, are different than optical telescopes. If I were to say X-rays to you, the typical thing you would think of would be an image like this, right? And what does this tell you? This tells you that X-rays travel through things, right? And so this tells you that a typical telescope, like you guys will have, will not reflect X-rays, right? Optical light will nicely bounce off these mirrors. X-rays will travel straight to the mirror or get absorbed in the mirror itself. So we have to build a different type of mirror, a different type of telescope to be able to look at X-rays. Here's what the Chandra X-ray mirrors look like. Instead of having a surface that you have the X-rays coming, that light coming straight on and reflecting off, the X-rays come in almost parallel to the mirror surface, and they come in and they have bounce off, and we call it grazing incidents. They graze off the mirror here, they graze off the second mirror here, and then get focused 10 meters away onto the detector. Of course, with a ground-based telescope, typical optical telescope, if we want a larger collecting area, as you know, we just make the diameter larger, right? Here, to make a larger collecting area, because they're conical, we can just put more and more mirrors around the outside of them, right? So we can just build up nests of mirrors to be able to increase our effective area. And so Chandra has 4 nests of mirrors. The mirrors are made out of glass, and then they're coated in gold and iridium, 2 rather expensive metals that actually turned out to be really good at reflecting X-rays. Glass is heavy, gold and iridium are expensive, limits how big you can build the reflecting area. It's fit inside the trunk of a space shuttle to the launch, and that was really limited, the length of this and the mass of the mirrors that you could launch. The detectors at the end are CCDs, so they're not so different from the cameras that you all have in your cell phones, except that they have a filter that blocks out optical light, and so they're sensitive to X-rays. And so what do? Well, we use Chandra and XMM and other X-ray telescopes to look at the X-rays coming from material in these accretion disks they're falling into black holes. And we use a technique that we've developed called X-ray reverberation mapping that uses echoes of light to try and map the inner regions around supermassive black holes. So here's an artist's impression of a black hole with an accretion disk around it and a jet that's shooting off from the black hole. And this jet also shines down on the disk and irradiates it, and we try and look at those echoes as light from this jet bounces off the disk and comes towards us. Right? This is not so different from hearing echoes in a cavern, right? So you stand in a cavern, you shout your name, you hear the echo. If you measure how long it is until you hear the echo, and you know the speed of sound, you can figure out the size of the cavern, right? Same principle that sonar on the ocean floor works, right? You can figure out, by looking at an echo, how far away it is if you know how fast the signal is traveling. Right? So here we're looking at X-rays, so the signal travels at the speed of light. So we know the speed the signal is traveling at, and so we just have to be able to measure the time delay between light coming from this region here that shines down on the disk and light that reflects off this accretion disk. And so we do this by looking at emission from the element iron. So iron is one of the most abundant elements in the universe, and it actually emits extremely brightly in the X-ray part of the spectrum. And so it emits an energy that's 6 kiloelectron-volts. Its emission looks something like this, and its emission is shaped the shape of its emission is shaped by the gravitational effects caused to the black hole. So we look at the variable light that's coming from the X-rays coming from this jet, and we look at the variable light that's coming on this ion line, and we try and measure the time delay between the two. And by doing that, we can say, if this time delay is 1,000 seconds, then I know that the average distance between these two regions is 1,000 light seconds. Right? So you have to have a measure of how big this region is. We did this for the first time in 2012. Here's the data. This is the time delay in thousands of seconds against energy. This black line shows you the energy of the ion line in blue. If you look at blue, you see that there's a delay that sits right at this ion line energy of about 2,500 seconds. So we're actually able to say that the region between the base of the jet and the accretion disk is about 2,500 light seconds. And what does this correspond to in terms of size of the event horizon? This is something like 7 times the size of the event horizon for a maximally spinning black hole. Right? So we're looking at really right down, close in before things fall into the black hole. Okay, so I have a little animation. At the time when this came out, NASA did a little press release for us. So hopefully the sound will be on this animation because the a nice commentary that goes along with it. So let me see this work.
This is the supermassive black hole at the center of NGC 4151. The dark object in the middle is the black hole. Surrounding it is a flattened cloud of dust and gas called an accretion disk. Recently, scientists using the XMMNewton X-ray satellite showed that a mysterious source of X-ray flares actually lies high above the disk. About half an hour after each flare, the inner accretion disk lights up with an X-ray echo. The delay is caused by the time it takes light from the flare to reach the disk. This is the first clear measurement of the effect, and it demonstrates that the flaring X-ray source lies well above the disk. With flares serving as flashbulbs, future X-ray telescope missions will be able to use their echoes to precisely map the environs of distant black holes.
So, since that first detection in 2012, we've now managed to do this in about 20 supermassive black holes in the nearby universe, and learned a lot about what happens as things fall into black holes. But we made another big discovery just earlier this year that made it onto the front cover of Nature, where we actually saw a black hole system evolve in real time by looking at stellar mass black holes. These are black holes about 10 times the mass of the Sun in our own galaxy. This black hole is called Massey J1820, and we use this same X-ray reverberation technique to measure time delays. And instead of measuring time delays of the order of thousands of seconds, we're now measuring time delays of the order of milliseconds, because this object is millions, something like 1 million times less massive. So this made it onto the front cover of Nature, and this was using data from a new mission, relatively new mission called NISA. NISA is an X-ray mission that sits on the outside of the International Space Station. NISA stands for the Neutron Star Interior Composition Explorer. This is an image of it in the lab. This was built at NASA Goddard Space Flight Center. It's about the size of a washing machine. And each of these 56 things is what we call X-ray concentrator optics. They're basically crude X-ray mirrors that focus the light down onto an X-ray detector. This was launched to the space station from Cape Canaveral on a SpaceX Falcon 9 rocket in June 2017. Here I at the launch. I got my SpaceX hat and the SpaceX VIP badge. I got to go in restricted area where they had a sort of party essentially for the people and members of the team. It was the 100th launch from the same site that was used for all the Apollo missions. So Buzz Aldrin was there, gave a talk. We were all getting excited. 30 minutes before launch, and then there was lightning. Within 10 miles of Cape Canaveral, so the launch was scrubbed for the day. I had to fly back to Detroit, and I missed the actual launch. My buddies who stayed there said the best bit of the whole thing was seeing the secondary part of the rocket re-land. And hearing the sonic boom as it comes back down. But this made its way to the space station, and it's an excellent mission. It's got extremely good X-ray timing capabilities, so it's really good for X-ray reverberation. Here is the Dragon 9 capsule from the Falcon. From the Falcon 9. That's when it's attached to the space station. Here is NASA, and here is the Canadarm robot pulling it out. This is obviously extremely speeded up. You can see the reflections of the clouds from the Earth on the shiny surface there. And here is an image from one of the high-resolution cameras that are on the outside of the space station. So you can see the space station solar panel, and here is NASA pointing towards an object, either likely a neutron star or a black hole. And so what did we do with our nicer observations of this black hole MAXI J1820? Well, we tried to answer a question about how black holes change, or how the accretion disk around black holes change as material falls down to the black hole. And there was a bit of debate for many years about whether the radius at which the accretion disk, or how close the accretion disk gets to the black hole changes, or whether this thing that we call the corona, or the base of the jet, changes in height. Right? So observations were unclear as to whether the disk comes in and out, or whether the corona goes up or down. Right? And so our observations were able to break this degeneracy and conclusively show that it seemed that the accretion disk seems to stay in place really close to the black hole, and that the jet, the corona, seems to change in height throughout as material falls into the black hole. And for those of you who are data junkies, I will show the data. You don't have to understand it. What I should show you here is the spectral data. This is essentially brightness versus energy. Each one of these lines is a spectrum taken at a different time. You can see that they all fall on top of each other. And it's the width of this line, the shape of this part of the line in particular, that tells you the location of the accretion disk. You can see it's the same, right? So this tells us that the accretion disk doesn't seem to change. Over here are the time lags shown as a function of temporal frequency. Again, you don't have to understand it. All you have to see is that the lines don't lie on top of each other. Each of the different colours is again taken at the same time as the spectra. Time lags change. That tells us that the distance between the corona, the base of the jet, and the accretion disk changes over time, whereas where the accretion disk is doesn't. So this corona is going up and down, and the black hole is staying where it is. And so that's what we figured out about stuff falling into the black hole. Okay, so I'll stop there. So it's an exciting time to study black holes. We now have the first direct image of black holes using sub-millimeter telescopes doing interferometry with the Event Horizon Telescope. Of course, one thing I haven't mentioned at all today, which of course is extremely exciting, is the detection of gravitational waves from black hole mergers, which is an entire separate talk on its own, of course. And I've tried to tell you about our efforts using these X-ray reverberation techniques to learn about how things fall into black holes as they gobble up material surrounding them. And I'll stop there. Thank you.
What's the time frame for this change in the coronal height?
Yeah, Yeah, so these observations were taken over a period of about a month.
Okay.
So typically these are, we call these black hole transients because they turn on, they get bright, and then they turn off. They're often observed by AAVSO actually, right? When they typically turn on for weeks to a couple of months. Some of them, one famous one called GRS 1915 has been on for almost 30 years. But most of them are turn on and off for a few months.
Fast one and then a little longer one.
Okay.
Martin Rees, is that Martin Rees that had that photograph? The one earlier said Rees 1984?
Yes.
That was Martin.
That's Martin Rees, yes, absolutely, yeah.
The other question is the earliest thing that you did had to do with the speed of light, and this particular one was doing in 1780s, whatever it was.
1783,
yeah. And the speed of light was really determined by early Romer, but he didn't have the actual speed. How did he figure out the speed of light? Because it didn't take until the late 1800s to really establish.
They had some estimates of what the speed of
It was
light
all
was,
estimate,
right? So we just used the best estimate at the time.
Okay.
And so that number that we quote is 500 times the sun, say was 500 times bigger, would have a escape velocity of the speed of light based on the speed of light that it had at the time.
At the time, which was 140,000.
And you suppose that some of the gravitational effects we attribute to dark matter, do you suppose that just maybe some of it can be attributed to black holes?
So this was an idea that's been around for a while. They're called machos. There's a massive compact halo object, like macho. And the alternative idea is WIMPs, weakly interacting massive particles. Right? So WIMPs versus machos. Right? You can test the machos quite easily because they should do what's called gravitational microlensing. So anytime a star passes behind a macho, one of these black holes on the line of sight, you'll get gravitational microlensing and it will become slightly brighter. And so there have been surveys that were started, I think, in the 90s, looking for these sorts of things. And you cannot account for the amount of dark matter that's required from macho alone. I forget the number, it's something of the order of just a few percent at most can be accounted for by macho.
Interesting.
Maybe I missed it, but did you give the size of M87, the event horizon?
Yeah, the black hole is 6.5 billion solar masses. In terms of kilometers, I don't recall, I'd have to calculate it for you.
But in terms of angular size in the sky, how big is the M87 event horizon versus the Sagittarius?
Yeah, it's like a factor of 2 bigger, I think.
Okay, even though it's in a separate galaxy?
Yeah, it's because it's 1,000 times more massive.
It was 22 micros versus 42.
Yeah.
A couple of years ago, while I was still working at Wayne State, I'm a crystallographer, I had the opportunity to hear Kip Thorne
Yes.
give a talk. 2 years later, he got his Nobel Prize because LIGO worked. Okay. What he did was, at the time, he complimented a physics professor at, oh God, I forget which university, it's close by.
Oakland.
Oakland.
Yeah.
In any event, he said the fellow was doing computational modeling, and he was using, or he had to be using the Weyl tensor instead of something simple like the Schwarzschild tensor. I wonder, do you do any kind of calculations like that?
No, I'm purely an observer, so I don't do any of the theoretical calculations in terms of obscure theories of gravity or any of those sorts of things, or even calculating lots of stuff Kip Thorne does, of course, is calculations of emerging black holes now, right, and what they should look like. So totally, there are a lot of people doing that stuff. It's not what I do. So. But David Garofalo, I think, is the guy's name.
I think I'd like to go in and sit in on his class.
Yeah.
I'm retired now. I got plenty of time.
Why not?
I'm writing science fiction.
Yes.
The black hole in our galaxy, it doesn't have an accretion disk, why it's dark?
Doesn't have an accretion disk, no. So it's not there is some gas around there. So we actually see there's radio light that comes from there. There's a little bit of X-ray light. So there is some gas that's falling in, but it's accreting at a rate that's something like 1 million times or 10 million times less than objects like M87. Right. So
It's a function of a particular size black hole, is that what it is?
no, it's just a function of what material is there, right? So if a star gets too close to the black hole, it can get tidally ripped apart, and suddenly you have a solar mass of material falling onto the black hole.
Okay.
There's many, many times less than a solar mass falling into the black hole at Sagittarius A star.
Let's do one more,
Anybody?
or 0 more.
One more?
Yeah,
Go ahead.
did Mitchell know light would be attracted to gravity in 1783?
No, he just
yes.
said what would happen if
Okay.
an object had escape velocity greater than that.
All right, let's see.
Thanks so much.
Last month's, the May issue.
Well, Dr.